Okay, everyone, good afternoon again. This week we have Alptekin Hoca from Graduate School of Informatics from our university. It's our pleasure to have Alptekin Hoca with us. He received his PhD degree from University of Surrey. He co-founded a company called Visio Prime after that, working on intelligent video systems for security, and worked as a senior research engineer there at that company before joining METU in 2007. He's an NVIDIA Deep Learning Institute certified instructor and university ambassador. He was a visiting researcher at Microsoft Lisbon. Then he was on sabbatical leave at the University of Birmingham in 2016. His main research interests are video surveillance, computer vision, machine learning, deep learning, and GPU computing. And today he's going to talk about an important problem, a challenge in deep learning, the problem of vulnerabilities of deep networks and adversarial attacks. So it's really going to be an interesting talk, and it's our pleasure to have Alptekin Hoca with us. The screen is yours.
Okay, thank you very much for Sinan Hoca for his kind introduction, and all the ImageLab coordinators for inviting me. Today, I'm going to talk about some vulnerabilities of the deep networks. And then we will also have a look at adversarial attacks, which are some crafted methods to fool these networks. So I have many slides, but I think we have limited time, so I will not be able to go into detail in some of those. But if you're interested, you can always contact me about more information. So I'll very briefly start with some basic vulnerabilities, okay? Because, I mean, deep networks are, I mean, we think them as solving many important problems, and they are really good at solving these computer vision problems. But they also have very interesting, some small kind of issues, if you like. So I'll start by looking into their vulnerabilities against some transformation, very basic transformations like shifting the image, rotating the image, or adding some kind of unexpected information into the image. And actually, I'll start by showing you this. This is from a paper by Richard Zhang from Adobe, published in 2009 in ICML. And he showed that actually, okay, we think that these networks are shift invariant. So when we shift the image, it will still be able to detect, classify that image correctly. And that's the main assumption. I mean, these networks are shift invariant. But he claimed that actually they are not invariant to small shifts. So if you shift them just a few pixels, you will be able to fool the network. And he shows that in here, actually on the left-hand side, you see the classification getting wrong in many cases. So this is the confidence of the network. And in some cases, when this turns into some other color, it means that it's classifying it incorrectly. And I'll show you why it is. But then they proposed an improvement to solve that. So an anti-aliased network. But I don't think we will have much time to look into that. But actually, this is an important observation, and there is some truth in that. But when we tried to replicate this, it didn't work very well. Okay, it worked very well with AlexNet, and when we didn't do augmentations, but when we used a relatively more advanced network like ResNet 50, and when we trained it with random resize and crop augmentations, we realized that it becomes robust. Actually, you see that we still shift the image, and we can classify it very nicely. So, okay, so this shows that these networks are vulnerable to small shifts, but there's a very simple solution to that. You can do augmentation, and you can basically solve that problem without even changing the network architecture, or you can change the architecture very slightly by adding an anti-aliasing filter, and you can also solve it that way. But it is still important, I guess, that these networks are kind of vulnerable to such things if you are not careful. Okay, so I'll show you why this is so. I mean, this is from our paper. This is from a very early work of mine. Actually, not regarding deep networks, but kind of shift variancy of convolution filters. You know, these networks are mainly convolutional networks. So we have like a convolution operation, and then we do some kind of downsampling, pooling, or we do convolution with a stride. Effectively, it is kind of downsampling the data. So what happens if you do a shift in the input, if you apply a shift to the input by just 1 pixel? So when I apply this convolution filter, the original result is this. But if I just shift these pixels, 1 pixel to the left and 1 pixel to the top, I guess the output is completely different. Okay, this is because we are applying a stride or pooling operation. So effectively, if you keep doing this in the network, in the end, a small shift might result in a completely different output. Okay, so these networks have this vulnerability because they have this downsampling operation. And as I said, you can even solve this with shift augmentation, or you can solve it by adding a kind of filter, low pass filter to here, so that you will kind of reduce the effect of this kind of downsampling to a negligible amount. Okay, and you can also utilize that because shifting the image results in different outputs, right? So that was one of the idea that we used in this paper, cycle spinning GAN for raindrop removed. So we adapted this methodology and we kind of embedded this into a GAN architecture. And the main idea here is that basically we use the shift variant nature so that different inputs will give us different outputs. So what we suggested was to do something like this. So we have our input image, we shift it by a predetermined amount. Well, this is not shifted, of course, this is the original one, but then we shift it by 1 pixel vertically, 1 pixel horizontally and vertically, and so on. So we use different combinations, and we feed these different combinations into our algorithm. And in this case, this is a GAN. And then we also undo the shift with the respective amount so that we align the outputs once again. Then we combine these. In this case, we do averaging, and we have a clean image. So what this does is a very simple thing. As you can see, we now have many outputs of GAN, which are then fused together. So we kind of benefit, make use of this idea. And when we test it, actually, we tested it on a specific problem, the raindrop algorithm. So your input image has raindrops on it. And then we apply a raindrop removal GAN. And we also apply the same algorithm by doing cycle spinning, the algorithm that I explained in here. And we see that actually we can obtain kind of sharper outputs. And also the quantitative results also show that there is some improvement on that. Okay, so here, as I said, I mean, the network has a vulnerability. you can either solve it or you can kind of apply it to, you can kind of make use of it to improve your kind of results. Okay, we then also applied this to object detection, and this is still an ongoing work. Actually, this is our earlier results, but we're about to do these tests more extensively. But just to give you an idea, here actually we have our ground truth images, and these are the confidence levels of the object detection algorithm. And when you have raindrops on the image, the confidence levels drop, and sometimes it even forces the network to classify and detect the still detect the object, but not identify it correctly. But when we apply cycle spinning, we were able to kind of get better object detection results, especially when the images are noisy. In this case, images contain raindrops, but this is a generic algorithm, so we could also apply it to other kind of noisy inputs as well. So here are some quantitative results as well. So we were able to get kind of better MAP results when we applied cycle spinning. And one thing I forgot to mention is that you can apply cycle spinning during the test only. So you do not change your network training stage at all, but you do these shifts and merging idea in testing only. Or you can kind of train the network by kind of using all these shifts during the training as well. And we realized that actually doing it also during the test training stage improved the results slightly more as well. Okay, then this is regarding the kind of shifts, small shifts in the network. Also, some works report that the networks are kind of vulnerable to image rotations as well. So we also investigated this property. So basically, we rotated some images and fed into different types of networks. And again, the literature was right. When you apply rotations with some, especially with large amounts, in this case, we apply, I think, 75-degree rotation to this image, AlexNet is fooled easily. So it misclassifies in many cases. So in this case, it misclassified the image, even though it hasn't changed at all, just rotated. It was mistaken for a kite. And again, that's good. But again, that's not showing the whole picture. Because when you try this with more advanced networks like ResNet 18 or ResNet 50, you realize that they are very robust to image rotations. So even though you see many kind of examples in the literature like that, when you apply it to more modern networks, they are quite robust against rotations. And also, again, we use data augmentation, and in data augmentation as well, we apply rotations. So we kind of feed the network with these alternative images as well, and network starts to learn to generalize its misclassifications against rotations, and it becomes more robust as well. So I would say that these networks are pretty robust to rotations, especially the new ones. But if you look into older networks, then you may still have this problem. And another basic thing we wanted to try was adding some distracting information to the image. And actually, we realized that even adding a simple grid, so adding a kind of simple grid structure, just some black lines to the image, is sufficient to confuse the network. And actually, we realized that when we apply this, many of the images are classified as window, because there are some windows with this kind of grid type of architecture. And then we excluded those classes, and still we get kind of these misclassifications. Okay, so this does not have a much research value, I guess, but we just wanted to see, because of curiosity, if we could fool the networks. And you can easily fool the networks without any sophisticated algorithm by just adding grids. And I think I don't have that example, but when you look at activation maps, you start to see many activations around these grids as well. So this also shows that these networks are kind of vulnerable even to small stuff that humans are not. So humans are quite kind of adaptive in that sense. I mean, we don't care if there are grids on the image, if they're slightly blurry, slightly noisy, but these networks behave completely differently in such cases. So still, I think it shows that we are not kind of replicating the human vision, but rather using some kind of algorithms, and they are kind of they can behave quite strangely compared to the human cognition. Okay, then these are the basic kind of transformations, but what about something more sophisticated? If we really wanted to fool these networks, we could kind of introduce some kind of noise into the image, because we know how these networks work, so we can kind of push them the wrong way. So we can add some noise to the images, which we call adversarial perturbation, and with these noise, we can obtain adversarial examples, so which look like kind of legitimate images to humans, but they are misclassified by the networks. So basically, we can do something like this. So this is a famous kind of image, I guess. So we have like a panda image here, and we add some noise. Generally, the noise doesn't need to be this big. This is just for illustration purposes. And when we add the noise, even though it still looks quite nice, and humans would not misclassify them at all, the networks could classify them incorrectly. So our idea here is that basically, how can we find such perturbations to fool the networks? And this is becoming an area of research itself. And actually, there wasn't much research like 3 years ago about this. But nowadays, you can see almost every day a new paper about creating adversarial examples. Okay, and let's have a look at some basic definitions about these adversarial attacks. Basically, we can have a black box attack. So basically, we can assume that we do not have any knowledge of the model itself, target model itself, the architecture, how it was trained, and so on. So we try to attack it without those information. Of course, this is kind of harder. Or we can assume a white box attack. And in that case, we assume that we have access to the model parameters. So we know the network itself, and we can access to the network and fiddle with it, basically. Okay, we do not modify the network itself, of course, but we use that knowledge to create some examples. And some other definitions are, nowadays you will see that either these attacks are non-targeted. So basically, we don't care to which class it misclassifies, as long as it misclassifies. So we can have a non-targeted attack. Or we can have a targeted attack. In this case, we try to fool the model to make a predefined prediction. So in that case, we choose the target class as well. So if we have a dog image, we may want the network to say that this is a cat. So we try to push its output toward the cat class, not any class. Okay? So this is called a targeted attack. And the performance of these attacks are generally measured by the fooling rate. So percentage of how much the target model makes mispredictions on adversarial examples. And also we use some metrics. I'm sure most of you are familiar with those, but generally some of these are not used in many other domains for as a metric. So let's try to have a look at them very quickly. So we can have like an L0 metric. That's the total number of changed pixels. So it doesn't care with how much magnitude they change, but that's the total number of changed pixels. L1 is the sum of changes in pixel magnitudes. And L2 is kind of related to this one. This time it's sum of square change in pixel magnitudes. Or another metric is L infinity. That gives the maximum magnitude change in pixels. So you only take the maximum change into account, not the sum of them. Then let's have a look at how these adversarial attacks work with investigating the most simple methods, FGSN. So this is I guess, the first method attacking the networks proposed in the literature. And it uses a very simple idea here. So it basically tries to do the inverse of backpropagation. So we still do backpropagation, and this time we try to feed it feed the gradients all the way back to the input. And while doing that, we do not modify the network weights as we normally do, but we kind of modify the input. So we kind of try to find the input that maximizes the cost rather than minimizing the cost, as we do during training of these networks. We try to maximize the cost so that we do this kind of operation. So we have our cost function here, and we calculate the gradient. We find the sign of the gradient, and we do not have a minus here because we are trying to maximize. And we multiply it with an epsilon constant. That's the user selected constant, specifying the magnitude of the attack. And we do that, and basically we calculate the loss of the logits with respect to the true class, calculate the gradients of the image with respect to the loss, and by this way we calculate the perturbation at the input that needs to be added to the original image, and we just take the sign of the gradients. We just take the sign of the gradients because sometimes the gradients will be small, but all we want is to push this to the wrong direction. So we just take the direction information into account, and we try to push it that way by multiplying with an epsilon. So this is a very simple idea. And this is one of the most popular kind of attacks still in the literature, because it's the most basic one, and it is the first one, but it's not going to be giving you the best results, because as you can see, it's not trying to kind of minimize the error, and also it's not taking into other classes into account. It's just trying to push this class out of its classification area. So lots of other kind of adversarial attacks has been proposed, and FGSN was this basic one. Then it has been improved and generalized to meet L2 norm, so to take L2 distance into account, and it became FGM. Then also people proposed some iterative methods as well, because it's not really effective to do it at one shot, but you can apply it iteratively to with small step sizes, for example, and by clipping the intermediate results after each step, so that you are still in an epsilon neighborhood of the original image. So basically, this is FGSN method applied in such an iterative manner. And then people also propose other stuff like projected gradient descent, PGD. So again, this also tries to contain the perturbation and tries to keep it small. And then these are kind of more advanced methods, Deep Fool and Carlin-Wagner, but they are based on the same basic idea. They're basically aiming for minimal perturbation, and they are trying to solve a optimization problem. But this time, different to the other basic methods, this time they are also looking for the closest hyperplane, and they are trying to push the kind of classification results towards the closest hyperplane, so that it can, when it crosses that boundary, it will be classified as that class. So basically, these work by finding the closest hyperplane and calculating the minimal vector and projecting onto that hyperplane. So you will see that these produce much fewer, much more pleasantly looking images. And they result in much smaller noise. And here is one of our outputs. Actually, we also developed a tool. We haven't made this public yet, but hopefully in the next 6 months or so, we will make this tool public. It allows us to apply different attacks and analyze its effects on the image. So when you apply, for example, a Carlin-Wagner attack on this, and when this was misclassified, you can see that the perturbation is very small. So, for example, this pixel has been perturbed by this amount in RGB space, and in YUV space, it corresponds to that. And in this area, it hasn't been modified at all, and in this, it has been modified with a very small amount. You can see that the pixel changes are just have a magnitude of 1 or sometimes none at all. So Carlin-Wagner attack is very effective, but as I said, it's an iterative method, and it runs an optimization algorithm. So even though it is very successful, it will take a long time to arrive at the result. So this actually defies the purpose in some cases, because to be robust to adversarial attacks, generally what you want to do is adversarial training by feeding lots of adversarial examples during training as well. So with Carlin-Wagner, actually, this is a bit difficult, because it's not impossible, of course, but it is more difficult because it takes a long time to create those images. Otherwise, I guess this is a very effective attack, and the results are very impressive. Okay, and then actually recently there has been other works, other interesting works. So rather than going too deep into one of these, I would like to show you a number of different kind of ideas as well. So one idea is one pixel attack. So they are, in these type of attacks, they are trying to perturb one pixel or a couple of pixels to change the prediction of a model. So they try to pick the best pixel. In this case, in this example, They are using differential evolution optimization, and then they show that in CFAR10, with changing just a pixel, you can change the deer into an airplane in this case, or cat into a bird misclassification. This is kind of a proof of concept. In my opinion, they are not as versatile as the other type of attacks because they do not work well for all classes. And another limitation is that, as you can see, this has been shown on CFAR10. You know, on CFAR10, we have 32 by 32 data, and we have only 1024 pixels. And we are just changing one pixel. But in ImageNet, you will have much larger images. And in that case, generally, changing a single pixel is not sufficient. So you may want something more than that. So while they are good food for thought, they are not applicable to real life as the other types of attacks. Okay, then I'll move. Okay, so there are many attack toolboxes as well, but I'll not go too much deep into that because I don't think we have time. But I'll just say that Clever Hans and Fullbox are the most kind of cited ones in the literature, and they are the most mature ones. So in our research, we also use kind of these and build on top of those because they already come with many attacks implemented in these toolboxes. Okay, then we have these adversarial attacks, we have these one-pixel attacks, and another idea is spatially transformed adversarial examples. And in this example, in this case, what they try to do is try to calculate a flow. So rather than adding a noise to the image, they kind of try to calculate something like a motion vector. But of course, there is no motion here. We only have a single image. And they try to calculate that to fool the network. So they want to use those motion vectors to replace the pixels with some neighboring pixels. And this is another example, this paper. And when you do that, actually, this also works remarkably well. And actually, it shows that with the standard attacks, this is the activation map of the network still looks into the correct part of the image, but with the spatially transformed adversarial examples, they make it look to some irrelevant location in the image. Okay, so up to now, actually what we talked about was adding some noise to an image, but that noise is calculated individually for each image. Another line of research in this adversarial domain is universal adversarial perturbation. So in this case, basically, you try to find a single noise, single adversarial example, a single adversarial perturbation rather, and you add that to any class, and that class would be misclassified. Okay, so rather than calculating noise separately for each image, now we calculate it for a simple single network, if you like. Not strictly true, but so here basically it works by like that. So again, we try to find a target perturbation and trying to misclassify, make the network misclassify. And we have an upper bound. So again, we try to push it to kind of some small value. So we don't want it to get too large. And here are some examples that we obtained. So this is the original image, and this is the activation map of the network. And we calculated a adversarial perturbation on ResNet 50, and we calculated that using only 0.78% of the ImageNet training set. And we obtained this perturbation. And as I said, this is independent of the image. And whenever we add it to any image, it will try to force the network to misclassify. And in this case, it is the adversarial example here, which is this plus this. And as you can see, the activation map gets kind of distracted now. So rather than looking at the correct part, it is kind of looking all around. Okay, and here are some examples as well. And depending on your loss function, what you maximize, actually the UAP will change. And that's one of the things that we are looking into. But I don't have too much results to show yet, but I can show you one result where we use cross entropy as the loss function. And in this case, it seems that the network, when it tries to misclassify it, and in this case, we use a targeted kind of attack, and it kind of fools the network by secretly embedding the target class in the image. So when this is the original image, and when we add it to add this noise, you have this result that you can probably see something looking like a fish in here, and I think it's called Tange. So it makes the network misclassify not by kind of by actually increasing the likelihood of this target. Okay. And in this, in the paper as well, in the original paper of the Universal Adversarial Perturbation, you see that the authors are saying that these are not kind of noise. These are not seen as a noise as the network, but these are kind of like a image-like features. So in these cases, we are doing some kind of like adding image-like features into the image, and because they become the dominant ones, the network starts looking into the target class that we are pushing it into. Okay, so this mainly covers the adversarial attack kind of universe. And you may ask why we need what can we do with these adversarial attacks? Okay, I think there are two main uses of these. One of them is using them in CAPTCHAs. So basically, you know, these CAPTCHAs are getting more and more frustrating. If you are like me, you may find it sometimes difficult to find the correct answers. So in this case, for example, you can see it's asking for images with the cars, but it is adding lots of noise. The reason is, okay, they want people still to be able to identify the cars, but they want to fool the network. So the network should not be able to find, so that the robots will not be able to pass this test. So basically, if you add CAPTCHAs with some noise that are not distractive to the humans, but rather distractive to the computers, then the CAPTCHAs will be much more effective, because the people will not be frustrated because the noise will not affect their judgment. It will not make it more difficult for humans to detect the objects in the in the image, but it will make it more difficult for the computers. So basically, if you can find some adversarial attacks with some nice quality to human perception, then that's a very nice use of that. Okay, so we will not be able to go too much into detail of that, but I would suggest you have a look at this nice YouTube video, which explains the main idea and the history of the CAPTCHAs. So that's one idea, and the other idea that you can use, other field that you can use these adversarial attacks is trying to understand how these networks work. So this is going towards the explainable AI. Because when you try to create these adversarial examples, you try to break the network. So when you're trying to break the network, you have to understand the inner workings and also how they come up with some decisions. And once you understand that, you can kind of break them. And it can be used the other way around. So once you understand them, actually you will have a more explainable kind of AI systems, and also you can build upon them. Okay, but at the moment, what we are working on is kind of creating nicer looking adversarial examples. And this is the main idea about our currently ongoing TÜBİTAK 1001 project called Increasing Visual Quality of Deep Learning Adversarial Examples. So our aim is generating adversarial examples having lower perceptible noise levels. But here we also stumble onto this problem about the metrics. So generally we use L2 metric or something like PSNR, but they might not be fit for the purpose, because as I showed you at the beginning, adding a grid will increase the L2 significantly, but they are not destructive to humans. So I believe that's not the correct metric. So for this purpose, of course, and we can also go back to human judgment on what looks good and what doesn't look good to humans. Okay, and in this project, actually, what we are trying to do is adding less noise, or less perceptible noise, rather. And we are trying to do that by these three ideas: adding noise only to the relevant part of the images by and not adding to the irrelevant parts. We try to optimize in YUV color space rather than the RGB color space, so that we can control the amount of noise added to illumination and the color channels. And also we would like to exploit the sensitivity of networks to small shifts. So by also applying some small shifts, again, this is not destructive to humans, maybe we can fool the networks. And one of our outputs can be shown with this example. So here are some example images we created. This is with FGSN attack, this is with Carly Wagner, and this is with MIM attack. And as you can see, okay, these are not bad, but for humans, the most destructive thing is this colored, the rapid color changes. And the color changes are between different colors. It's not smooth, okay? And this is kind of destructive to humans. So in this work, actually, we thought that we can apply the attack and try to optimize it in YUV space rather than RGB space, so we could disentangle the illumination and the color, so that we can kind of keep the amount of attack into the color less compared to the luminance, and luminance is more important for the network as well to classify the object, so that we can produce nicer looking images to humans. And we published this work, I think, last year, and we are still working on making this kind of better, and hopefully we will have some better results to show in next 6 months or so. Okay, I think we are about to get the end of the time. So I'll finish by showing you some other research that we're doing. So I'll show you some nice examples. Again, this is kind of related to the universal adversarial perturbation idea. And this time, we are using a pre-trained network and backpropagating it in the gradient direction, maximizing a specific class score. So I like to call them Uber samples. So for example, in this case, we try to find the input that maximizes the bee class. It's a honeybee. So we try to find the input that maximizes that class. And basically that image looks like that. So when you feed it to the network, it will, with very, very high confidence, it will say that it's a honeybee. So that's why I call them Uber samples. Okay, so this is not something we turned into research yet, but we created some kind of examples like this one as well. So this is the Uber Panda. So basically, if you feed it to network, it will be giving it will be classified as Panda. But we also started to see that this also shows the dataset bias, because as you can see here, you do not only see Panda features, but you also see the bamboo leaves as well, because in the datasets we use in the ImageLab as well, we have lots of kind of background information, and our datasets are biased because you do not have a Panda in office environment. It's always around bamboo trees. So basically, the network features are not robust in that sense because they learned not the Panda features only, but the surroundings as well. So as I said, this is not kind of a research output yet, but it also shows another vulnerability of these networks, this time because of the dataset and dataset bias. And here, this is the B example as well. And again, here you also see B features kind of here, but we also see lots of flower-like stuff because all B images contain flowers as well. So basically, this is another kind of research, I believe, how we can prevent dataset bias. So to conclude, there is still a lot more that we need to understand about these networks, and they still have lots of vulnerabilities. But this also leads to many research opportunities. So we can either try to fix these vulnerabilities for better performance, or we can also try to fix these for more generalization. So as I said, these will not lead into generalization because when you put a bee into an unusual environment, it will not be detected. So you can try to make them work in a more general sense. And another research area, as I mentioned, is explainable AI. So we can take all these information and try to kind of explain why this network made this decision, and if we change the input, why it would make the other decision, and so on. Especially this is important in domains like health, where you want kind of an explanation of how the network kind of came up with a conclusion. Okay, that's it for now. I think there was a lot more to talk about in each of these subjects, but I wanted to kind of keep it, rather than going too deep in one subject, I tried to show you the whole universe of adversarial domain, and thank you very much for listening.
Thank you, Alptekin Hocam, for this nice presentation. I think adversarial attacks are really important, and we need to somehow learn to deal with them. For that reason, it's really important to know them. Any questions from the audience? Otherwise, maybe I can ask one general question, maybe one specific question. So, what would be your comment regarding the other side? So you are working on models that can better fool networks, but how can we develop better models that can be robust against such adversarial attacks? So can we design a model that is robust against all adversarial attacks? If not, what does this mean in terms of the applicability, widespread use of deep learning methods in practice?
Well, I think that's more like a philosophical question in one sense, I guess, because you can always fool a network if you understand how it works. So you can kind of try to push it the other way, as in here, we know how it works, the cost function and so on. So we know what it maximizes. So we run it the other way around, and we can fool the network. So in one sense, actually, you can fool any network by kind of reverse engineering. But it is also, but is this a big thing? That's, I think, the second part of your question.
Yeah.
It may not be a big thing because in many cases, these networks work very well, okay? And we are looking into some kind of extreme scenarios. And I think, for example, Carlini, I think, one of the inventors of the Carlini-Wagner attack was claiming that very strongly. Okay, we can fool these networks, but who would like to fool it? I mean, this is like a very, I mean, this depends on the use scenario, but if you think about an autonomous car, okay, we can make it see a stop sign as a something else, and it might not stop. But it means that someone going and kind of fiddling with the stop sign and putting a sticker on it and so on. And if you are going to that distance, you can also do lots of other things physically. I mean, you can punch the, you can put a hole into the car tire and do something like that. So it is getting more like a philosophical question. So it depends on how safe you want to be. So these networks actually work very well in many cases. If you want to fool them, you can fool them, but how much you would like to sacrifice? I mean, if you try to, and another thing is it's like a impossible case. You fix a hole, but then you cannot fix all the holes, and there will still be holes. Okay, of course, this is a very big postulation. Maybe I shouldn't say that, and maybe you can fix all the holes in the next few years, and it would be a kind of perfect network. But at the moment, it seems that when you kind of fix one thing, people could attack in another way and still fool it. So fixing it for one attack is kind of, in a sense, futile, because there will be other types of attacks as long as people want to kind of fool them. So I think it's a very, very good question, and it maybe deserves like discussing for an hour or so.
Yeah, well. Sure. Yeah, definitely. So this, I know that this is not solvable. Actually, there are papers proving theoretically that you cannot obtain both adversarial robustness and good accuracy. If you get better robustness, then you lose in terms of accuracy. But if you want accuracy, then you need to live with adversarial vulnerability. It's really interesting. And I'm especially worried about the cases where, I mean, the stop sign, for example. I mean, maybe you can also, someone can just go and, remove the stop sign, and it is a physical attack, right? So you cannot prevent that. So, but the thing is, we don't see visually, we don't see these attacks, and we don't know when they can come and what would be the consequences. So maybe for widespread use of deep learning methods, we cannot make them perfectly robust, but probably we will have some certificates of robustness to some types of attacks, for example. Then, in addition to accuracy performance of networks, you will have some certificate of adversarial robustness with that as additional metric, and in addition to the runtime, running time speed, etc. So I think maybe we will have such kind of universal robustness metrics. This is really really interesting. If there are no questions, I think we can stop recording and continue informally. Would that be okay? Okay. Let me stop recording. Thank you again, Alptekin Hocam, for this nice presentation. We will continue.
It was a pleasure.
Alptekin Hoca'yı